get this started. The BC command is a very simple algebraic calculator. So you can say A equals 6, B equals 8, or B equals whatever. And then say C equals A times, all right, take it easy. See you next week. A times B, and then you type in C and it gives you the answer. Okay. Very simple, straightforward calculator. This particular calculator supports lots of precision and very advanced math. There is tools that are more modern and more accurate, not more accurate, but not quite so cryptic to use. But the reason I like using BC in this particular class is there's this function that we have called I base equals 10, semicolon, O base equals 2. What do you suppose this means? Just making a guess.
Changes your base number from 10.
That's right. It changes the radix. So basically you're going base 10 to base 2. So now that I have an input base of, let's go 34, there's my output base of 34 in binary. Now, how do we know that's true? How do we do binary? Yeah, we got 1, 2, 4. Yeah. You remember things. This is good. So starting with the least significant bit, okay, we're basically saying 2 raised to the first, or 0, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. And in this case, we're not stopping. We just keep going. Okay, we can go as many bits on this as we want. But when we were playing around with hexadecimal, we were stopping at 8 bits. There's a reason for that, and we're going to get to that also tonight. We're driving home some of this binary stuff because eventually I want you to design a 4-bit adder for me using logic gates. Okay, so we're going to go through all the math. You need to learn how to do that. And then we'll go through the circuits we need to do that. And then you're going to use ChatGPT to figure out if you did it right or not. And the thing of it is, you won't know if ChatGPT is lying to you because you won't know anything about an adder. So we're going to have to learn enough about an adder to know if it's working or not. So we're going to kind of vary up this exercise that in the labs where we use ChatGPT. So basically it's, 1, 2, 4, 8, 16, 32. And so we can see how we want to put this together. So our answer is 34. We have, is that something doesn't look right there. 2.
That's correct. That's a 32 and a 2.
It's what?
It's a 32 and a 2.
It's 32.
Plus the other 2. It's a 1. Right? It's a 1, 2.
So you got this should.
It's 2.
There should be another 0. It should be 0 or 1. So if it's odd, let's try 33. We'll see if my base is behaving. Yeah, that's right. Okay. All right. I'm having a brain fart. Okay. So we're moving between our decimal types. Now we can also do this. We can use our up arrow and say, make our in base 2 and our out base 2. So now we can add and it gives us our adding function. Okay. We can also do subtraction and addition and division. Now, you now know how to check your answers. What we're going to spend some time doing tonight is learning how to just do the binary side of things. Okay, by doing lighting lots of ones and zeros on the board. Okay.
We'll start with some easy numbers.
So if I have this and I want to add this, yeah, that's pretty simple. It's just straight addition, right? So here and here, that gives me my answer. So I could do over here, I could type in 10 plus 01. Ah, I didn't make a mistake. Surprise, surprise. But what if I wanted to add this? Yeah, we get our one and one is one with a carry, right? And then we get one and one with a carry. So we'll get that. See if that works. I said 11 and 1. Ooh, what'd I do wrong?
Should be 1 0.
Yeah, that should be a 0 for the carry.
Yeah,
It should be when you have 3 ones lined up, you end up with a 1. Yeah. A little rusty on my binary here. Okay.
So 2 1s is 0.
Pardon?
So 2 1s is 0, right?
Yeah, because the way it works is just like in decimal, when you get to 10, you put the 1 on the next column. The same thing happens here. When we get to quote 2, we do a carry. Okay. So do a couple more of those. Let's do 101 and then let's make well, let's do it like this. Let's do a 111 with a 0 0 1. And you can see how this works, right? 1 and 1 is going to be 2, but we don't write 2, we write 0. We carry a 1. 1 and 1 is 0. Carry the 1. 1 and 1 is 0. Carry the 1. Yeah, let's see if that worked. Go back and check our work here. 111 plus 0 0 1. And lo and behold. Now, using what you know about base 10, let's do the very similar. Just make sure. You know what? That doesn't even show up on the whiteboard. Oh, well. So I'm using what we do with base 10 here. Let's take 1 0 and subtract 0 1. Just like in decimal, we have to do the carry part. We got to borrow, bring it down. Okay. All right. So what are we getting? So it's the other way to do this in your brain is saying, okay, what is this in binary and subtract it? You can, and then change it back into binary. You can do that. That works. Okay. Because this would, in decimal, this would be 2 and 1 basically, which would leave us a 1. So yeah, let's let me clear my screen here. It doesn't look like there's a clear command, so let me just close my terminal. Type in quit. Clear. And then I can put my iBase 2 base. There's a history, but it's only for the session. iBase goes 2, iBase or O base equal to 2. And then I said, put minus. There we go. And then you can pad the zeros and everything. So this is basically addition and subtraction. Now, do you want to try walking through multiplication and addition? Sure, why not? That's why we're here. We're here to get our brains stretched. Now, I found this really cool website and I want to bring it up because they teach a very arithmetic way to do it. It's called Binary Math Info. Pretty straightforward. And what it's doing is that this is actually written for kids in grade school where they're learning ones and zeros. They're not learning about computing. They're not learning about anding and oring. They're not learning about anything but moving numbers, ones and zeros. So basically, they are doing math in binary. So there's nothing to do with assembler here. It's just math. Okay. All right. Binary subtraction, multiplication. And notice the patterns they're using here. This is called binarymath.info. So feel free to bring it up. And you can see, and you go through the same thing that you do in base 10. Same exact process. It's just you're dealing with ones and zeros. Okay. And you're all saying, how does this relate to me? I will get to that. Okay. It does. Okay. At a very personal level. It's on your cell phone. And then it explains, you do this, you take one times this is that, and one times this is this, move the zero over, then you do your addition, and then there's your answer. Now, we can do the same thing. So we want to multiply 101 times 11, see what we get. Use the pound sign or the splat times. And what do we get? The same answer. So we can actually check our work on here using the BC command. Okay. Now let's look at the division. Now the way they're showing division here is, I personally have never seen division done in binary like this. So yeah, this works. This is like teaching your grade schoolers long division using binary. Thinking about the poor grade school kid that can't learn long division to save their life. And now you're going to give them ones and zeros to do the same thing? Ah! Patience to the parent. Okay. And it's basically showing you how to walk through this process. I want you to keep these processes in mind. Is this how a computer adds? No. Is it how it divides? No. It uses a completely different way to represent binary. One's complement and two's complement. You don't use one's complement much anymore, but we do use two's complement. It's how data is stored. And when we add or multiply, divide, we do shifting. We move things left and right. So binary math in a computer is not this. This is binary math on a piece of paper, just like base 10. You would do the same process if you were in base 6 or base 8 or base 29. And believe it or not, you can calculate in base 36, which is the 24 letters of the alphabet and the 10 digits. Yeah, that's a lot of fun. You can do that. I think it supports this. Yeah, we'll see if it's iBase, OBase supports 36 as a base, just for fun. I don't know if it does or not. I'll say 36. And then I'll just pick a few numbers. Maybe not. Maybe it needs to be upcase.
Seems to like it when I did I base of 10, O base of 36. I was programming.
Oh, there you go. So it will convert it. That makes sense. So if your I base, your input is 10, output is 36. I actually worked on an inventory system that had this kind of craziness. And
I don't think it's used.
yeah, so you can use, so we'll use uppercase. So there's a lot of different numbering systems out there. But now, how does this apply to you? This is where we're going next. On your computer, I want you to open a command line. And type in IP A, whoops, lowercase. And then look for an IP address that has 10.18.163.16 something. It's going to have 10.18.163 as the first three, okay? Look for yours. Compare with your neighbor. They're all different, okay? Now we're getting into a little bit of the meat of why binary is so important in the world of computing. An IP address, we talked about how they work. I got 10.18.163 and what I have, 60 something, 69. Okay. And that's one number. And then there's this big long number here. This is all hexadecimal representation of our MAC address. And these funny FFFFFs is our net mask. Given an IP address, given a net mask, you can find the first and last IP address in your subnet. Does that sound like networking? Yep. Does that sound like something you need to know in networking? Yep. It's all ones and zeros. Okay. And I'll briefly show you how this works. Okay. So where is mine here? And this is my broadcast. And then my net mask is, that's, where is it? It's 255.255 F. Anyway, I know what it is, so we'll write it out. So here's how this works. Using your calculator that you just discovered, set your O base to 10 and, I base to 10 and your O base to 2. Okay. So I want I base 10 and out base 2. Then what I'm going to do is convert these into binary. Okay. So I'll use, I'll start with 163 just for fun. Notice it's only that. It says this is a, it says it's 10. Ooh, that's terrible. Okay. Let me die. 10, 0. 1. And we know what 10 is going to be. Now, the way we represent these numbers is our hexadecimal. Remember hex? We have base 16. So basically, we have 8 bits allocated to the number 10 here. 1, 2, 3, 4, 5, 6, 7, 8. So what numbers do I need to get a 10? Well, I need a 0, a 2, a 0, an 8, and a 0, 0, 0, 0. That gives me 10. Remember that binary decimal quiz that I give to every single class? That's what this is. It's groups of 8 bits that are your IP address. Okay. So, and we can do 18, which is going to be, so the way I do this is, okay, if this is 8, that's going to be 16, right? So 16 and 2. Did I get enough zeros in there? One too many. 1, 2, 3. 1, 2, 3. There. That's this one. That's this one. So you break it into groups 4. And our 169, 163, we got O base, and it says this. But here's where our problem is. It's sort of right. Okay. It's mostly right. Okay. So if I have 8 bits, and if you all remember your binary decimal quiz, 2 through 4, I have 1, 2, 4, 8, 16, 32, 64, 128, and 256. The easy way to do this is say, okay, 256 is too big, so I can use a 128. Subtract 128 from this. That gives me something, right? Come on, help me think. Trying to keep you awake here. Okay. Use your phone, quick. Pardon? 37? 33. 33? 37?
35.
35. Going once, going twice. So we have 128 and 35, which we're going to drop down to 32 here. So we got 0. Whoops, 32 is the last bit. So a 32 from 35 is going to be a 3. And it looks like that. And we do this process again for 69. Okay. And 69, I'm going to leave blank for a second. Our net mask that it didn't display here is this. 255, 255, 255.0. In hex, it's simply written FF, 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 0. Or blank, depending. So the way the net mask works is all the ones go here. And it goes all the way across. So our 256, our 3 255s, I should say, they're all right there. And then this last one is 0. So when we put our 69 in binary, which is going to be 0, 0, 64, and then 0, we don't need a 16. I need a 9 and 5, so I need a 4 and a 1. 4 and a 1. Then these are zeros. That's what the net masked. Now you're asking, why do I care? This is how networking works, folks. Our net mask puts these bits, our first 3 octets, into the same subnet. So I can talk to anybody on what is it? 10.18.163 subnet. Okay. And the way that is notated is 10, 18, 163.0/24. 24 is how many bits are in your net mask. And then now that I'm doing this, I'm going, okay, this is great. Why do I care? Well, it tells me the first and last IP address of my subnet. And the way this works is when I say 1 and 1 is 1, right? It's still 1. I'm ANDing all these. And then the way ANDing works is you have to have 2 1s to get a 1, right? So if I only have 1 1, it's going to give me the same answer here, right? 0 0, and then I'm going to have all 1s where there's 1s. So when your network is going out in 1s and 0s, this is how it knows how to route. This is just one facet of the binary system that's used in computing in ways that who knew? Okay. So using ANDing is how you find your beginning and ending IP addresses from your net mask in an IP4 system. Okay. All right. Wanted to show you that. Now, what I want you to do is go look up 2's complement. And you can use Wikipedia or whatever you want. What it is. Two's. Okay. So why is this important? Well, we have positive and negative numbers that we deal with in computing. Well, how would we represent a negative number? Yeah, it's like, oh, well, yeah, that's what one's complement is. It's still out there, but not very much. Most everything is 2's complement. So basically what it is, it's a way to store your data. So when you calculate it, you know if it's going to be a negative or positive number. Okay. All right. So when we have 2 complement, and we'll talk about different signs here, we'll use 8-bit. So when we get up to 255 in our IP addresses, do we have a negative IP address? Actually, no. You'll never see a negative 128 or a negative 16 or a negative 10. That means it's unsigned integer stored in 8 bits for networking. Okay. What about negative numbers and hex values for your color scheme? I've never seen them, but that doesn't mean they're not there. Okay. Where do we see this? Floating point. How do we get floating point and how do we represent floating point in binary? This has been one of the big headaches of the AI world taking so much energy, is that when you calculate your back propagation trees, they're using floating point arithmetic to give it a weight. So the stronger their floating point is with more decimal points, the more accurate your LLM gets. But that takes a lot of juice to train your model, which is why everybody and their brother is getting into small nuclear power plants. That's where I would start investing. is don't invest in NVIDIA per se. Invest in the companies that are making small, very highly effective power generation for companies like Oracle and Google and Microsoft. Microsoft just bought 3 Mile Island. That had a nuclear meltdown, right? Well, they're going to turn that thing on with Microsoft's money, and Microsoft gets a bunch of power out of 3 Mile Island. For what? AI. To do what? Calculate floating point. You want to be a trillionaire? Invent a way to make LLMs just as accurate using integer arithmetic. You'd be a trillionaire overnight. Okay. But you would kind of need to know about this binary stuff. Okay. All right. That's 2's complement. And basically how it works 1 to 0. Okay. Now, in the book that most of you haven't even cracked open yet, that I have given you in 273, we go to the main page, the Raspberry Pi computer org, and we talk about computer arithmetic. They are talking about computer arithmetic the way computers are doing it. This is not the same as what I just showed you with binarymath.info. Okay. Because what happens in our world of computing binary is we have this problem with a carry bit. What if I only have 8 bits and that's it? Okay, that's it. I've got 8 bits and I add 8 bits, but I end up with a carry bit. What do I do with it? Throw it away? There's an old movie some of you may remember called Office Space. Anybody remember that? The red stapler? Go watch it. It's great. It was made pre-2000. So it was these guys got together and they wrote this code that found the floating point mistakes and it made a deposit into their checking account. And then before they knew it, they had more money than God. And all of a sudden, the FBI is searching for them. And this is based on a true story because I actually met some people that did this. They were working on ATM machines using Csci, and Csci has rounding errors. So they just summed up all the rounding errors. And when it got to a nickel, he made a deposit into his checking account. He was thinking he might get a nickel a week. Well, he got like 5,000 nickels a day. Well, and security says, where are all these nickel deposits coming from? He was updating his resume. So it's out there, and there is problems with floating point. Okay. Where was I going at? Well, anyway, the movie was about that. It was just a lot of fun. Anyway. All right. So when we do this, we have to worry about the carry. Now, his book goes into the stuff you'll need to know as a 4-year student when you take your computer organization. This assembly language thing is just the beginning, okay? There's another class after this that's way more intense than what we're getting into, okay? I'm just showing you how all the binary kind of fits together and makes computers do its thing, okay? So then we get into, there's these exercises. I recommend you at least look at them. The answers are all right there. Just click on them. You know, I'm not going to give you a quiz and have you copy the answer, for heaven's sakes. Why waste my time and yours? Okay. All right. Unsigned. Now, this is one thing I've noticed in the students coming in. This, I can tell I've been teaching a long time, is that there's the stuff you need for the grade, and there's an extra little oomph you need for the job. That extra little oomph, I don't see much anymore. Okay? So it's like I need more and more of the grade things to help you realize that there's a lot more to this to jump over to become good in this field. It's just getting broader and broader, and there's no shortcuts. It just takes time and practice. Okay. and then the carry flags and how we use the carry flags. Okay. Now, what I want you to do, or what we will kind of be working on together this evening, and at least for the next lab, is we've been talking about ones, we've been talking about zeros. How is the one made?
Transistors.
A transistor. A simple transistor. Okay. And I'll start with a really simple circuit. It's called the flip-flop. Digital electronics is fine. Virtual labs. Let's see. There you go. Remember all those truth tables we put together that you completely forgot? Well, here's how you put together a flip-flop. Why do I care? This is how memory is stored. This is how memory is stored in your RAM. So when you turn your computer off and your RAM purges itself, you lose everything that's in RAM. Coming to a future near you, RAM, you'll take it out and you'll replace it with something. One of the technologies is called a memristor, a memory resistor. You put it in and it functions like RAM, but then if you turn your machine off, it maintains state. Imagine you as the programmer never having to worry about a write. You just save it off. It's going to be there when you reboot. You would never have to write it to disk. Do you think that changes the model of how you would think about computing? Just a little bit. And there's another one I like to break your brain on, is imagine all the code you've written. You can't use if ever again. How would you write code without an if? You can do it. Does it make code a little more reliable? Well, it depends on your argument. In functional programming, which is a model of abstraction for programming, you don't use if. And most of you are going, what? That hurts. Yeah, that hurts. There's a good book, 7 Programming Languages in 7 Weeks. And each programming language breaks your brain in a different way. Okay. So anyway, these do not maintain state unless they have a circuit, and it's called a clock. Remember your clock speed on your computer? The faster the clock speed, the faster your computer runs. Well, those clocks are synchronized with things like RAM and the CPU, so it knows when your ones are ones and your zeros are zeros. So if your clock, for some reason, degrades or stretches out, you start getting errors in calculations and in RAM. And this, you will generally, you don't have clock errors, but you will have memory errors of some sort. And that's just the transistors wear out. Okay. And in this case, we have a NAND gate and a NOR gate, and we just put it in, and this basically what goes in, it stores it. And the clock pulse keeps it alive. Okay. So a flip-flop is made of ones and zeros that get pushed to our gates. Okay. All right. Let's look up this one. Schematic of NAND gate. I want the actual schematic of, this is telling me actually want to find is the ones and zeros or the logic components, discrete structure, discrete. Too advanced for what we're doing. So we want there's your schematics. A little hard to see. In fact, it's a lot hard to see. But basically, here's what you have is in your NAND gate. Or here we go. We'll just start here. This is a transistor. Here's a transistor. That transistor has 3 little pins on it. Okay. The middle one is the gate, the switch. And then you have your input and your output. You put a 1 here, and you put a signal on this, the output becomes 1 or not. Okay, there's different kinds of transistors. And then you usually have a pull-up resistor and then some sort of power supply to power it. Okay, I know there's cleaner things out there. Oh, you know where it might be? Let's see if I can find it. I think he put it in his book, Crash Course in Computer Electronics. In the Pi book. Okay. There it is, Crash Course in Electronics. Okay, here we go. This is in your free book that I sent you. Okay. This is what's going on when you run your computer. You have AC and it gets converted. And then we have all those things that we have to do. And here's an example of turning something on or off. So I have 2.5 volts, and then here's a resistor and another resistor, and it's measured in ohms. If you've ever taken basic physics, all this is why you need basic physics. And you know, if you're transferred to a 4-year CS degree, you're supposed to know all this stuff. Okay, that's where it comes in. Series and parallel, and then how it works in parallel. I won't go into great detail, but then there's the capacitors, and then light switches and how it works. Okay. This is the actual hardware that creates the ones and zeros that you put into your logic gates. Those logic gates are then added together to create your CPU and your RAM. And now you have your computer. So it all boils back to this ones and zeros, and putting it in this big picture is, okay, why do I need to know this? Here's the answer I got from LinkedIn. I polled my former students. How many have used assembler? Basically, the answer was nobody. What did it help you with? Troubleshooting. Is it hardware or software? Step 1. Sometimes that's really hard to know. Now, okay, it's not software, it's in the hardware. Where in the hardware? How do you know if it's not RAM? Or how do you know it might be a disk drive? How do you know? What kind of tools do you run on this stuff? Computer science is about problem solving. Find your problem, cut it in half, work on the half where the problem remains until it goes away. Ta-da! You're a genius. That's it. Okay. All right. Now, here's what we're going to do. Taking your knowledge of everything I've smashed into your head tonight and this semester, is your next lab is you're going to draw me a circuit using gates. Okay. Not this. You'll be using gates like this. Okay. I want you to create for me a 4-bit adder. I've given you enough information to know how to check it if it's right or wrong. And yes, you can use ChatGPT, but if the answer's wrong, that tells me you never learned it in the first place. Okay, that's really simple. So the next lab is create a 4-bit adder. And I recommend, if you would prefer, or if some of you don't like working in teams, I find it elevates the game a little bit. People who work in teams have a tendency to learn more and get a more correct answer. A 4-bit adder is pretty straightforward. You might even find a few answers out there. But how do you prove it? How do you know it's going to add correctly? Well, I gave you a tool called BC, and you know how to add ones and zeros now. So you can put it together and see what the output is and see by and large if it worked or not. Because a 4-bit adder is pretty straightforward. It's not real difficult. Okay. So you'll end up drawing some sort of diagram like this. That's your 4-bit adder. Okay. You may need 8 bits in, depending on how you want to structure it. Okay. So that's the next lab. And I will go post that on Canvas right now. Now, housekeeping. We finished our lab with all the C and the subroutines and the functions and calling all that and the make file. We will be revisiting that same idea, but we'll be using assembler. So we'll be doing very similar things, but writing in assembler. Okay. So we'll get through the adder thing, and then we'll be doing assembler and function, make files, and so on. So we'll be writing Raspberry Pi assembler. Okay. All right. So where's my, there we go. Let's go here. I will put that in here. So introduce yourself to your neighbor and say, hey, I want help. And work together and come up with a good answer. Okay. This dual back to the log again. That's such a pain. I gave you another week on last week's assignment because I realized some of you were really close to finishing but didn't quite get it. Okay, so.
I think the output is right here. So it's 8 and 4 out. Yeah.
All right.
I think it has a way to do it with that. Unless it's different here. It has a 4-bit under right. You're going to go to 5 bits. Just turn it off.
Those of you that have been helping me on the servers, do not give up. The parts are on their way somewhere. So once the parts come in, I'll send out an email, and all you'll need to do is bring a Phillips screwdriver. Any size should work, because we'll be putting the drives into the trays and putting the trays into the machines. And then I have an automated install that should work on the hardware. And then we'll install OSs, and it will rename the machines and reboot. And then we'll stack them in the racks. But we have to put in the runners so where the servers will actually fit. And then we have to wire them up. Okay.
Let's see.
These right here, I think these are just supposed to be where. So, yeah, basically where it's being like.
Number 7.
But how I'm thinking it's done. It's done here with the 2 bits, and then the other 2 bits, and then this 2 bits, and then this 2 bits, and then they're all squished.
Sometimes it's called a half adder. So it's either a 4-bit adder or a half adder in different books. And if you want to do a full adder, if you find this, oh, that's easy, I can do that. Some of you are going to say that. Okay. So either one.
So you can use this box to on this ladder, right? So we can use those boxes you have like this.
Okay, so that's what this is.
So this has the inputs. This is kind of like a simple, right? They have the inputs. They say, oh, we have this padding thing that's even output or whatever. But if they have the padders, you have to do it in to be able to actually do addition.
Okay.
So that is almost like, so you take each one of the squares and expand it once again. So that's like the overview blueprint.
Something like.
So that's what next lab is a combination of this.
Yeah.
Yeah. Well, basically, we're going to have 4 of those diagrams. 8 inputs.
Right.
That's not just every point. So we're not-
There's another way. Yeah. Unless this is actually not. See if it explains this. I would imagine this is something that became pretty simple. I don't think it would be. If people actually care so much, I know. I mean, there's something.
That user exploits yourself. The actual some of yours and put these two.
I was gonna say, I just saw this one right now, and it started clicking. They're all connected.
So this is gonna be loud.
I think the hardest part about this, at least for me personally, is just the proofing. I feel like. Yeah,
Six.
computer sure it's- Open this up and you get a- put parts around it. What do you?
You know what? Let me do this. Six.
Does everybody know how to put ones and zeros and get the right answers out of this? You'll need to know that. And the way this works is if this is my truth table and I put in a 0, 0, so X and Y is 0, 0, it goes through an AND gate, but then it's got this little bubble here. That little bubble means not. So this is a NAND gate. So in a normal AND gate, 0 and 0 is a 0. But because I have a not, it converts the output to a 1. That makes sense? And the same thing down here. Now, if I make the outputs of one into the inputs of the other, put ones and zeros and work your way through until you get to your answer. This is how you will know if you've got your adder right or not. And I just put it in the lab. It's easier going to find information on a full adder than it is on a half adder, because a full adder deals with the carry bit, which is kind of the takeaway on this lab anyway. What do you do with a carry? Okay. So you'll be combining different logic gates into your adder, and you'll take a particular problem of ones and zeros. You'll check it to make sure it's right, so you know what the right answer is. And then you will trace the ones and zeros through the circuit and see how it adds. Making a few leaps here, because I know you'll be using good friends ChatGPT, but this is just at that precipice that if you put the time in to learn this, you'll know what the right answer is on the other side of ChatGPT. That's the real job skill. How do you know when it's wrong? You got to know how to use ChatGPT, but you got to know when it's right and when it's wrong. So here's another example, okay? So you can practice walking through these. These are straight right out of the book, okay? And there's also a gazillion helps out there that have all this stuff. Draw your own logic, look for digital circuit electronics or something like that. You'll find all kinds of places where you can draw your own AND gates and NOR gates. I got a few of them laying around. See if I can find any. let me bring up this one. Here's one. This would be very handy for you to remember for your 4-year degree.
Yeah.
So this is really simple. They've got a couple on-off switches. What happens through the gates and which lights turn on? How would you know? Well, you write your ones and zeros and find out what they do at any particular point. Okay, that's a 1. Well, that's off, so that's a 0. So that would be a 0 and that would be a 0. And you kind of work your way through. That's all there is to it. Free trial. I wonder how long it's worth. Probably only works on Mac and Windows. Really?
Once everything's perfectly organized,
You gotta be kidding me. Well, ain't that slick. If you're a Python person, you can use py spice. And you can build your logic gates and write the code and have it do your adder. That's slick. The 2, 3, or 4 inputs. Nice. That's crazy. I'm gonna play with that.
You're gonna be sitting there wondering where the fuck your shit is. And you're like, oh, yeah. This function just should not look like that.
the general consensus is
It's definitely good for math, right? Which is super funny to me. 'Cause, like, John was like a toy ring with John, and it's like this huge.
it's like I guess I'll so like I said,
That's funny. Just kind of right. That's like a bunch of 15 inches, so I have that basis to work off of. That's not, yeah, I took this diagram. That's true. It's fun writing.
I think I got my first ever favorite grade that I was talking about math professor. Professor does me like attendance quizzes. Class. For the grades, I just don't care about it. It's a crystal.
No.
I went through, I did it totally wrong, right? And then I realized it for the time stuff, so I went through and started doing it the correct way. Except I went through and I couldn't remember anything, so I started doing guess and check. With derivative anymore. And so it's like doing guess and check. Well, I was like, just check two answers. I didn't know which was the correct answer, so I gave you a 3. And I was like, I have to give you the worst of the 2. And I was like, bro, if I had the wrong answer and the correct answer is obviously the second answer.
Yeah.
I just love it.
That's funny.
If there was the once.
I think so, huh?
So good.
Doesn't even matter.